I'm very happy to present Andrej Bogdanov, who was a postdoc here 20 years ago. And very happy to have him back. He's now a professor at Ottawa, used to be in Hong Kong for many years. And I met him when he was a grad student in Berkeley.
That's right.
Yeah, I remember you very well from that time. And you told me that Turkish has an infinite number of words.
Oh my God.
Mother is Anne. Remember this?
No,
And your grandmother is Anne, and then your great grandmother is Anne.
I don't remember this, but it's amazing. You really didn't know which room my talk was in, but you remember what I told her 20 years ago.
You have a language with an infinite number of words. So looking forward to today's talk with you on a different topic.
Thank you. Thanks, Irit. It's really great to be here, and I haven't been for a while. So yeah, so it's today I want to talk to you about adaptive robustness of Hypergrid Johnson-Lindenstrauss. And Irit said she wants to see all the technical details, and it might be a bit disappointing, but you can always try to get me right. One thing
you're still here until Wednesday, right? So anyone can.
One thing I learned from Avi when I was a postdoc here is that, you know, a talk is your opportunity to really cheat, and I take this to heart. So so it's your job to hold me honest. Now, when I gave this talk before, you know, I start asking by how many people know about Johnson-Lindenstrauss, but I'm a bit embarrassed to ask that question at the IAS, so I won't. So instead of asking you, I will just remind you what Johnson-Lindenstrauss embedding is. So, so you have a bunch of points in space, in some high-dimensional space, A, B, C, D. And what you want to do is high-dimensional space is a pain to work with, so you want to work in low-dimensional space, but you want to preserve the distances between the points. And if you want to preserve them exactly, you're out of luck. You need as many dimensions as you have points. And the big insight of Johnson and Lindenstrauss is that if you're willing to pay a small approximation error, then you can do a lot better. So what they showed was that if I take a bunch of points in high-dimensional space and I apply a random embedding to them, so what they did is they applied a random projection to a lower dimensional space, but I'm going to today talk about a variant of Johnson-Lindenstrauss, which was is due to indicate mod 1 later, where instead of doing a random projection, what they do is they apply a random matrix of independent Gaussians. So that's like I have n points, and then I apply this this matrix of Gaussians. And then I get some m-dimensional vectors, and the theorem is that if this is scaled properly, then this embedding is almost isometric. So it means that the distance between the points gets preserved up to a epsilon multiplicative factor, and you can embed an exponential number of points. So you can embed in m dimensions, and you can take any epsilon square number of points and preserve these distances up to epsilon. And this is great for many reasons, some of which I'll try to get into. And and it's been studied a lot, right? It's an important result. And it's the best you can do in particular, in the sense that no better embedding exists. Like for all kinds of settings of parameters, it's been proved that it cannot really be beaten. So why is Johnson-Lindenstrauss so useful? Well, it's useful for algorithms, right? For data science, right? So if I want to do something like a near neighbor search on some set of images, a natural sort of algorithmic approach is to, instead of looking at the image itself as some very large vector, first I embed it into lower dimensional space, and then I do this near neighbor search in lower dimensional space. So that's kind of a big algorithmic application of it. And you know, this is very useful. And in particular, there was a few years ago in 2021, there was this somewhat controversial technology that Apple designed, which they call the neural hash. And what they wanted to do is they wanted to know if your device contains some forbidden images, right? So they wanted to know if you have one of these things on your device. So in their case, it was they wanted to check if you have child pornography on your devices, right, to comply with some regulation. But this is, it's a minefield, so they had to do this very carefully. So they wanted to design some kind of secure way of doing it, right? And I'm not going to get too much into the security aspect of their design, but sort of their idea was, well, we're going to take the image and we want to have some very efficient algorithm to run on it so that even if I wrap some kind of secure computation around it, I can still do this fairly efficiently. So the way that this neural hash worked is that it used some sort of embedding, that it takes the original image that I want to test against some database, and it embeds it via Apple's neural hash, and then it does some kind of search to detect whether you have something like that on your phone or not. And sort of, you can imagine this became controversial for many reasons, but it's also kind of a nice bashing field to try to now say, well, how can we break it? And so this is kind of the idea, is that first I want to take the image and I want to hash it into something that's a lot lower dimensional, and then I want to do some kind of near neighbor search into my lower dimensional space. And this opens sort of the possibility of, if I want to now do some kind of attack. So what kind of attacks can you do on this neural hash? Well, what kind of attack is what I guess they call sensitivity attack in machine learning, which is that you can say, well, I have something which is illicit on my phone, and maybe I'm just going to change a few pixels in it and move it to something which is very far, which is not going to know. So this is what they call a sensitivity attack. Can I take my input and change like a few pixels, a few bits inside the input, so that after hashing it, it looks like it's very far, right? It's not. It doesn't preserve the distance. That's one kind of thing that you can do. There is another kind of attack which is more relevant for what I'm going to talk about today, which is an invariance attack. And here is sort of, maybe I want to implicate somebody that that they have something on their phone which is in fact not sensitive, but it looks like it's sensitive. So I might try to take some input and change it in many ways, like change many pixels into it, so that after I apply the hash, it still maps to something which is close to it. And these are things that you can try, and in fact, many people did it and tried it, and it was successful apparently. So this is not something I know that much about, but there is this quote from this paper of Bhatia and Meng where they say, well, they tried different attacks and they succeeded in implementing them, and then they try to explain why these attacks work. And so what they write there is that we make the surprising discovery that the neural hash implementation is approximately linear, which is a bit like the Johnson-Lindenstrauss embedding. And it says this actually enables a bunch of attacks. And in particular, it enables them to generate near collisions, which is this kind of invariance attack, taking an image which is very far and mapping it to something similar.
Why is it invariance? I don't understand.
I don't know why they use this word, but this is apparently the terminology that's being used, right? Before that, I called it expansion and contraction, but then it turned out that they have some standard terminology that they use, right? So I guess you want the output to be invariant. I don't know why they call it that. So let's try to figure out sort of what is happening here. Why is it that if you have a linear map, this enables some kind of attacks? So I'm going to focus here on the Johnson-Lindenstrauss embedding, right? So A is a random Gaussian matrix, and I map some high dimensional vector to a lower dimensional vector. And you can kind of start asking questions. Well, what is the worst kind of attack I could do? So in a sensitivity attack, what I could try to do is I could try to find two inputs so that I want to maximize like the ratio between the norm of the output and the norm of the input. I want the outputs to be very far, but the inputs to be close to one another. And you can do that, but in some sense you have some control when you design this embedding A of how bad the sensitivity attack can be. And in particular, the spectral norm of the matrix tells you what is the worst that a sensitivity attack can do. So if we forget about everything else and now we just want to prevent sensitivity attack, we'll say, well, we can do that by using a matrix of low enough spectral norms, like we can achieve by scaling or anything.
Don't you want this to depend on M?
Do we want this to depend on M? Okay, so the way that this is part of my cheating, the way that I set up this matrix A is that I think of the columns of having unit norm. So they're like random Gaussian entries of variance 1 over M, like in this notation. And that's the scaling I will use, but I'm not going to focus too much on the exact parameters.
Sorry, I have a question.
Yes.
Like this matrix, it's going to have a kernel, right?
Exactly. Okay. So you're asking the exact right question. So for sensitivity attacks, the kernel is not an issue, but for the invariance attack, right there, we want to find inputs that are we want to control like how much it can shrink. The kernel is a problem, right? The minimum, if we try to take minimum instead of maximum, we get infinity, right? And that's unavoidable. Like whenever you have a linear map and whenever you have a shrinking map of any sort, you're going to have two inputs that map to the same output. So now I'm going to try to convince you that it's still kind of an interesting question. And the reason it's an interesting question is that exactly because of what you said, right? If I want to find two contracting inputs, or even if I am given one input and I want to find another one with which contracts with that one, all I do is, right, I find something that's orthogonal to the image of this matrix that goes through the line or whatever that X is on, and they have many, many things. But you think about it like when you, in the very kind of, okay, so this is like what happens in the ideal mathematical world, but as soon as I implement this on the computer, my inputs are actually not arbitrarily real numbers. They're going to have some finite precision. So maybe like one model of what really happens is that the inputs live on some kind of grid, right? And in that case, at least we cannot get things to map. Typically, we would not get something to map to 0 because if A is a random matrix, there are not going to be any other points on this line, right? But then you can start asking questions, of course. Well, there are not going to be points on that exact line, but there are going to be points that are very close to that line. So what happens there? And that's the question that I want to talk about. Okay. That was an excellent question. And yes?
Is there other ways to get around it, like padding the input and then requiring that the inputs come from some special set? Or
I think the input and requiring that the input come from some special set, I don't know. It's a good question, right? So if you just pad it with zeros, well, I don't know. I mean, you end up using the, right? If you pad it with too many zeros, then it's not a contraction anymore, right? So you do want it to contract for like to be useful for data processing and so on. So somehow like I want to focus on this regime where it's, you want to have both of them. You want to lose some data from the input, but you don't want to be able to create this kind of collisions.
I guess we have collision resistant hash functions.
Good. So we have them. Right, but they're not really useful for this kind. Like you can create them by engineering them like very hard, right? You have this kind of SHA or whatever, right? You use over some like bits and finite fields, and you do some things, but it's not clear that those would have any. If I wanted to be an isometry, if I wanted to preserve distances, it's not clear at all that they would do anything like that, and they probably won't, right? So yeah, so you're getting at the kind of, you're asking all the right questions, right? In that, in some sense, we want a mapping which is useful for data, for embedding actual data that preserves distances in the data, but we don't want to be able to create too bad collisions inside this. Okay, so this is sort of the kind of one way to formalize the problem is that you have some Gaussian matrix which has M equals alpha n rows and n columns, where alpha is going to be some number less than 1, right? So it's going to...
That's much worse than Johnson-Lindenstrauss.
Well, okay, so you can let alpha change with n and then...
Almost one over.
Yeah. But yeah, so we'll see. So right now I want to kind of abstract from Johnson-Lindenstrauss and formulate it as a problem and see how much we can get. And the problem is that I want to find a couple of points now that are restricted to be integral, right, to line some grid, right? And it's important, it's going to be important that it's bounded, that they take values between minus b and b, right, where I think of b as some small number, where I want them to contract as much as possible. So this is what the attacker wants to do. They want to find the contracting attack. And there are 3 parameters here. There is this alpha, there is this b, and there is this kappa. And the question that we're interested in is sort of when can you do it, and when is it useful, and when is it hard to break? And this is what I will tell you. It's not a theorem, but yes.
Is there an interesting version of A being like over finite fields? I somehow saw the like linear hash is conjectured to be collision resistant.
It would be, but here I'm specifically interested in working with real numbers. Okay. Yes. Yes, good. So then you can sort of try to draw this diagram. You can write like different values of these parameters alpha, b, and kappa, and you can ask, when is this problem feasible? When is it infeasible? And somehow...
What is kappa?
Kappa is... Contraction. Yeah,
Okay.
how much I want to contract. So good. So let me for now think of b as being like 1, right? So I just want my input vectors to be -1 or 1 or -1, 0, and 1. So I have kind of this very like high dimensional, but like very few degrees of freedom in there. And then sort of what does this say? It says that when kappa is very small, when it's close to 0, like on this axis, I have log of kappa inverse, so I start from the top. Then statistically, collisions are not going to exist, right? Just because I'm working on a discrete domain, I cannot map things to be too close to one another. And then there is a point, and this is the point where it's about like 2 to the -1 over alpha, when this kappa is, when at least in expectation, collisions will start to appear, right? So I will have inputs that map to nearby output.
This is for random Gaussian matrix.
Random Gaussian matrix. Yes.
For dipole.
Kind of the most interesting thing that I want to talk about is that now there appears to be like this regime, right? So if I make kappa to be very large, then I have algorithms. Then not only do these kind of colliding pairs that contracting pairs exist, but I can actually find them. But to find them, like I need to make kappa, like for the algorithms I know, to be fairly large. I need to make it to be square root of alpha, not 2 to the 1 over alpha, but I need to make it square root of alpha. And then there is this whole regime in the middle where contracting pairs are going to exist, but I'm going to try to argue that they're hard to find.
Can you show what kappa is again? Sorry.
Kappa, this, okay?
Bigger than 1?
Well, it's like...
You wanted to, it becomes harder when it's small.
It becomes harder than it's small. When it's very small, when it's 0, it's impossible, right? When it's large, then you would expect their algorithms. So we'll talk about algorithms. And the point is like there is some kind of intermediate regime where there is evidence that it's feasible. I'm actually not going to prove that it exists statistically, but in expectation, if I take a random alpha, there are going to be many collisions, but they're hard to find. Okay.
What is the norm used here?
The 2 norm.
The 2 norm.
Yeah.
Although the grid is our infinite norm.
Yeah. So here we use the 2 norm to compare it.
So you think of alpha as constant or like polynomial in n or?
So Yeah, you can think of alpha as being polynomial in n, right? That's one kind of parameter regime. You can think of it as being square root of n or n to the 0.01, but you can also think about that being constant, right? So I will think about both regimes. So, but here it's kind of, yeah, the scaling. Okay, you're all asking good questions, and I don't have kind of perfect answers, right? You can ask about the whole regime of parameters. We have some evidence why it's hard when alpha is polynomial in n, and we have some other evidence why it's hard when alpha is like some constant, some small constant, and goes to infinity. Yes.
So you are sort of doing this JL transformation on like a particular set now, which is this grid,
Exactly.
right? Like,
good.
To what extent is what you're just going to say generalized to like an arbitrary set of a size like to the n?
It doesn't.
It doesn't.
Yeah. So this is specific for the hardness results are specific for the.
Like even if I gave you something that's like somewhat additive set.
I don't know. It's a good question. We haven't thought about it. We just studied it for the grid because in some sense we thought it's kind of the most interesting domain for applications. But those are all like excellent questions. Yeah. Okay. So so sort of let me give you a very concrete way in which this is hard is that, well, you can say one thing that's a bit annoying about this map is that it takes discrete inputs, but it gives you continuous outputs. Now, what happens if I round the outputs? Then I get a map from discrete inputs and discrete outputs. And there is some setting of parameters, like this is not, I don't know if it's optimal or not, I'm not going to focus it on too much, but in which this map is a shrinking map. So it takes more inputs than outputs. So we know that if it's a shrinking map, there must be two inputs that map to the same output after rounding, right? And then what this tells us is that even though pairs of inputs that map to the same output exist, not only are those hard to find, but actually finding any pair of inputs that maps to nearby outputs is hard to find, right? For some notion of nearby, right? And these are the parameters. So this is sort of a particular consequence of having this hardness.
There are better rounding schemes than just going to the nearest integer point.
There are better rounding schemes. Yeah. Okay. Yeah, I don't.
You don't use them.
We don't use them. We didn't really try to optimize the quantitative aspects of this result. It's a good question whether you can.
Well, dimension improvement in this better rounding.
Okay.
So
okay.
It can be meaningful to you.
Yeah, I have to think about it. So here we just use the, we just round it to the nearest integer or nearest in every coordinate. Whether you can do with better rounding, I don't know.
Form, yeah.
Okay.
I have another question.
Yes.
Like, does this problem become substantially different if you also assume that the entries of the matrix itself come from like a grid or like some kind of rounding? I mean, this is also what happened in practice, right?
The entries from the matrix itself come from some grid. Well, it's true, but okay, so I want to think of kind of the rounding error for the entries of the matrix as being much smaller than the rounding entry for the vectors in the matrix. So of the input, right? So I'm going to think of the input as being an image, right? So maybe the entries are like between 0 and 256. Well, if I round the matrix of Gaussians, then I would be rounding it, to the 7th or 8th digit of precision. Mm-hmm. So then I would suspect that it should still be true, right? So I don't know. So that's another good question. Like, to what extent, like maybe if the matrix itself becomes integral, then it becomes easier. So kind of qualitatively, I think once you start kind of making the entries of the matrix be integral, then you're looking. It's more like a lattice problem. So I think like we have some reason like why the hardness is inherited from lattice problems, at least in some parameter regime. So then you might expect it to also be hard but again, I don't know. Like now you're introducing a fourth parameter. So then I don't know how this fourth parameter will affect things. Yes.
Just back to this better rounding scheme. currently would be useless because you actually want to implement this, right?
Yeah,
And we only have
yeah,
exponential
yeah.
time algorithms for
Yeah,
these
it's
forms.
existential. It's just interesting what the parameter.
Yeah.
Yeah, I agree.
Yeah,
I agree.
there is no good algorithm to implement this better.
But when Max solves his open problem.
So compared to this empirical paper, which actually finds these pairs, how does it compare to your results? Does this contradict your results?
Well, I mean, it's first of all, the map they use is not like random Gaussians, I'm sure, right?
I mean, the
I just-
Apple
Yeah.
implementation.
Yeah.
Mhm.
It's not even completely linear, so they do something. So right, they found that it's approximately linear. I don't know. I mean, I suspect that if you try to, use this embedding in practice, there probably still be reasonable contractions. I mean, it's really good kind of theoretical result at this point. It's well, I will tell you a bit about like some experiments that we did, but we did not try anything that answers your question. So. Okay, so I have to give you a bit of meat. So sort of what we actually prove, right? And the no solution part and easy part, those are rigorous results, right? No solution just is some kind of probabilistic analysis that tells you that, if I make kappa very small, it's unlikely that any solutions will survive. And this part I want to talk more about. It says that if kappa is large, then there are interesting algorithms there. So I want to tell you a bit about what these algorithms are. And then once we get a sense about what kind of algorithms work, we'll go back and see sort of how we can argue hardness, right? What are our arguments for hardness? So there are two algorithms. They're kind of two natural algorithms to try. Well, before trying them, let me first simplify things, saying, well, why is a red herring here, right? If I find some contracting x which is non-zero, I'm done, right? It's the same problem. Modulo like the exact value of b maybe, but let's not go there. So this is kind of the problem that I'm going to talk about. I just want to find some non-zero x that contracts by a lot. So what am I going to do? You tell me. I think you told me what the algorithm is. Yeah. Kernel, right? So you try to find something in the kernel, right? But you won't find something that's exactly in the kernel because it's discrete, so you're going to discretize it, right? That's kind of the first natural algorithm to try. If you think for 2 minutes, that's what you come up with, right? So the way that you do it is that you sample a random x in the kernel, right? It's going to be, if A is a Gaussian matrix, it's some Gaussian, and then you snap it to the closest grid point, right? And, you have to do a bit of work if it's outside, then, but that's essentially the algorithm. And if you analyze it, right, then what you end up with is that it gives you contraction about 1 over b.
Where is alpha in this?
Excellent question. Where is alpha in this? This algorithm doesn't use anything about alpha. Like as soon as alpha is like strictly less than 1, even if I have a matrix which has 1 fewer rows than columns, this algorithm works. If I have a matrix that has many fewer rows than columns, this algorithm cannot take advantage of it. Right? So this algorithm kind of works well in the regime where alpha is very large, but in the regime where alpha is smaller, it doesn't really do much. It cannot take advantage of that. When alpha is small, there is another algorithm. And to explain to you this other algorithm, I have to kind of tell you about a different way of thinking about the same problem. So we're actually going to tie our hands behind our back and we're going to say, well, this matrix A, instead of looking at it all at once, suppose I give you the columns 1 by 1 in a streaming way, right? So these are the columns of the matrix, A1, A2, A3, A4, right? They're some kind of Gaussian vectors. And now your job is, now I'm going to simplify it a bit. So I'm just going to look for a solution which is plus minus 1, not between minus b and b. So you just need to pick signs for these vectors, right? So that when I take the sign combination of these vectors, I get as close to 0 as possible, right? So that's just a reformulation of the same problem. The signs are the columns of the matrix, and these are the rows. So how are you going to do it? Well, It's essentially like a poor man's version of an algorithm of Bansal and Spencer, right? So this is what you do, right? The first column comes to you, A1. Well, it doesn't matter where I go, right? I can either take it positive or negative. I take the positive one. Now I give you the second column, right? And now you have to make a choice. Am I going to take with a plus sign or with a minus sign? What are you going to do?
I'm going to take closer to the origin.
You want to be as close to the origin as possible. And that's the algorithm. That's the online norm minimization algorithm, is that you maintain a state, and at each point when the new input comes to you, you have two choices. You either add it or subtract it, and you pick the shorter one, right? The one that outputs the state to a shorter one. Okay, so how does this algorithm do? Well, this is the picture, right? At some point in time, I have this state S, and then I have this new vector AT coming. It's a Gaussian vector, so it's spherically symmetric, right? And what does this mean? It means that it has some component in the direction of the state, which is about 1 over square root of m in length, if I live in m-dimensional space. And then the rest is in this perpendicular direction, right? And this tells me, like, essentially how the state evolves. Like, there is some stochastic component in the evolution, but then there is some deterministic component in the evolution, right? In the direction of S, I'm going to subtract the parallel component, which has length about square root of 1 over m. And in the other direction, I'm going to add what the perpendicular component is. Right, and now if you think about how this algorithm evolves, is that when the state comes short, the perpendicular component is going to dominate for a while. But once the state becomes very long, then these two things will start to balance each other out. And one consequence of this is that when you run this algorithm, this is an actual implementation, this is what's going to happen, is that initially, like, this is the state on the vertical axis, like normalized by root m, it's going to grow, but then at some point it's going to settle. And you keep taking more and more columns, they're not going to change the length of the output. It's going to stay the same. In fact, you can write some kind of differential equation that tells you how this evolves, like when m goes to infinity. And it looks like there should be some stochastic component to this differential equation. And like for the longest time, I believed that this was true, but then I found like there was some error in the calculation, and this stochastic component actually vanishes. If I keep drawing these diagrams for larger and larger m, you get like some plain old boring differential equation that you can solve. And then what this differential equation predicts is that eventually, like, the relative norm of the output will settle around this beautiful square root of pi over 8. Okay, so that's what's going to be. It's going to be square root of pi over 8 times m. Okay, and that's a theorem for the case when this, well, it's not the problem we wanted to solve already. There was the simplifying assumption that the inputs are plus minus 1, that they're not come from the grid. But what happens is that the output is going to have length square root of m. Like even when m is much larger than n, the input's length is going to be square root of n because there are plus minus 1 entries. So when I look at the ratio, I get square root of alpha. And that's where the square root of alpha comes from. Okay, so that's what happens when I restrict myself to like plus minus 1 values. What happens if I allow my inputs to come from like a larger grid? Well, then it happens that I can gain an extra factor of b in the input without sacrificing anything in the output. So I get square root of alpha over b, like provided that alpha is like not too small compared.
So the theorem is this algorithm finds an x with this stretch.
Yes, yes.
So this is strictly better than the previous algorithm.
It's
the previous one.
It's better. Yeah, it's better modulo this requirement. So when m is very close to n, this algorithm doesn't work too well, right? when I have a matrix that is almost square, then the other algorithm will work better. So there's some sweet spot like that introduces some extra log factor, but the conclusion is that this is like up to this log factor, this is, you can do this for the whole range of parameters. Okay, so let me tell you now what this algorithm does, like how do I get this extra gain in this vector of B? And the main insight is that sort of you can let this, like going back to the ±1 algorithm. So first of all, what doesn't work? If I just scale this algorithm, it's not going to work because both the input and the outputs are going to scale by the same amount. But one insight is that if I scale it and I let this algorithm kind of roam wild at the beginning, right? The way that the algorithm works is even if I started much higher, if I started with some state that has larger norm, the dynamics of this push it towards square root of pi over 8. So eventually it's going to end up there. And that's the idea, is that somehow like we're going to let this algorithm roam wild at the beginning. Well, we're going to let it pick entries which are plus b or minus b. It pretty much doesn't matter what it puts in there, like only to a certain extent. And then we're kind of going to tame the state at the very end by using smaller entries. So this is this algorithm cool. So this is the picture of it, right? What's going to happen? It's like a cooling, right? I'm going to let it kind of heat up and then I'm going to cool it at the end. It's also an online algorithm. I keep picking entries for this vector x, and initially I'm just going to pick between plus b or minus b, just like in the ±1 algorithm, right? And then after I've done this for a while, I'm going to say, well, how many entries do I have left it to handle in the end, right? And once I get close to the end, I'm going to start turning down the heat, right? I'm going to say, well, no, I'm going to use plus minus b over 2, right? And then the same dynamics will say that now instead of converging to square root of pi over 8 times b, now it's going to converge to square root of pi over 8 b over 2, right? And then in the next few steps, I'm going to go down to b over 4 and b over 8. And then near the very end, I'm just going to use plus minus 1 entries, and it's going to truly converge to square root of pi over 8. So what you end up with some vectors, most of whose entries are plus b or minus b, but somehow you use these small entries near the end to make the output be short, right? I didn't write the code, but it's
Why
good.
do you get at the end? Why do you get 1 over b at the end?
Because at the end of this algorithm, I'm just going to run it with plus minus 1 entries, right? I'm going to kind of take this state and I'm going to make it converge.
It's because most of the entries in your vectors are b.
Yes, most of the entries in the vector are b's. So those are going to control the norm of the input, right? But the final state is going to be square root of m, which is going to control the norm of the output. So somehow you get the best of both worlds. Yeah. And that's pretty much the only thing that we do in this paper, right? Okay, so let me tell you sort of what else we say. So now is the question, now I want to talk about hardness, right? Somehow, like this was what Avi asked is, right? In all parameter regimes, we can find something that gives us square root of alpha over b. Now the question is, can we do better? Like, can we have an algorithm that improves on this? And now we have to start like, we have to we cannot prove theorems, right? We're in p not equal to np land now, so we have to start, making arguments, right? So what kind of arguments are we going to make for this?
Hardness statements are not theorems.
I don't know if mine will qualify, but this one is a theorem, right? So this is one that we can prove. Is that if you look at this regime where now like the matrix is very flat, right? So I have somehow n columns and something like n to the 0.01 rows, then we can prove that in this regime like roughly square root of alpha over b is optimal, right? So square root of alpha over b would be something that looks like this. It would have an n to the 0.49 instead of n to the 0.51, but like that's kind of what you get. And there we can prove that if you can find a better algorithm for this regime of parameters, that you have found an algorithm for finding short basis of lattices, so that you have some kind of hardness result from some well-studied problem. And in fact, like most of this work was done before, like there is this work by Bruna, Regevson, Gantang, where they reduce from this problem to something called continuous learning with errors, and then it's kind of an easy reduction from continuous learning with errors to this problem here. But then you do get your theorem, right?
So do you expect quantum algorithms to do better for a problem?
Quantum algorithms, no, quantum algorithms cannot solve learning with errors either, right? I don't know, like, so for this regime of parameters, at least you shouldn't expect them to do.
AI is not enough for you?
So this is the second kind of hardness argument, and the one that I think, like for me at least, is more interesting is, well, now what are we going to do with this other regime of parameters where kind of we worked hard with lattices, we couldn't get a reduction, we still want to know why this algorithm is hard. And then there is this kind of physics sorcery called the overlap gap property that they say, well, we use this to predict why certain problems are computationally hard. And what they tell us, right, so now I'm just going to invoke, I'm not going to try to justify, is that what predicts hardness is something about the structure of the solution space of these problems, right? So if I think of sort of all, like the space of all possible solutions or all inputs X that map to like short outputs, right, these are some kinds of vectors, right? And they say it has something to do with how this space is connected, but there is this specific criterion that they say that, like, if the solution space doesn't have these kinds of configurations, then the problem is hard. So what are these kinds of configurations? They're these kinds of umbrella configurations. They're like, if I think of these solutions as being vectors in space, having these vectors so that like the normalized dot product between all pairs of them is roughly the same, this predicts computational hardness, right? And I'm going to, okay, so I'm going to state this at face value right now, but then I'm going to try to argue why, at least in the context that we discussed, it's somewhat sensible to do.
So in the cases that such umbrella configurations exist, it is clear why there is an algorithm?
No, they say there is no algorithm.
No.
So if it doesn't exist,
If you lack umbrella.
if you like umbrella, no, that's much less, it's much less clear. So here is one sort of argument, is that if I just take an umbrella consisting of two vectors, right, then having some kind of range of forbidden range of parameters for the dot product between the two vectors, somehow they say, well, the algorithm has to jump over this range. But if I slowly start changing the input bit by bit, right, it has to at some point jump over this range. And this can be formalized for some classes of algorithms. I'm going to tell you how they do it for online algorithms, right? So you can argue, you can use this to kind of rule out some subclasses of algorithms.
So also for local algorithms, low degree algorithms.
For local algorithms, for low degree algorithms, it's not as simple as it sounds. Like there is some ifs and buts there, but yeah, so this is some kind of general criterion that then you can use to rule out various classes of algorithms. And I didn't put it, so maybe I will tell you how it's done for online algorithms, but so let me tell you, okay, so first of all, here is sort of what the result is that these umbrella configurations do not exist, right? If I take a large enough umbrella, right? If I take enough vectors in the umbrella, for roughly the right range of parameters. So there is this extra log factor here, but if you are willing to disregard this log factor, I get the right prediction, which is that kappa is like square root of alpha over b, right? And again, there is some assumption on the relative order of kappa and b. So I would say, you know, this is probably not the final answer, but it's some indication why.
So what is this? This is showing that your algorithm doesn't contradict their prediction?
Yes, so that your algorithm, that the online algorithm doesn't.
And improving
Would contradict.
Yes. Good. And again, like this is not something we invented. There is this beautiful paper by Gamarnik, Perkins, Kizildag, and Shu, where they do this for b equals 1 essentially. They do it for the infinity norm, not for the 2 norm, but it's an extension of their argument, right? They use this. So in particular, you get this consequence that for online algorithms, like the one that I showed you, it rules out that these algorithms can do better. So it says that there is no, you need to make some extra assumption that the algorithm is norm concentrated. So in my algorithm, I kind of told you the magnitude of the entries that you pick. You have to agree ahead of the time what is going to be the norm of X before you run the algorithm, right? This I don't know how to, it's some technical issue that I don't know how to resolve. But if you look at this kind of algorithm, then you can rule it out unconditionally. Why you can rule it out unconditionally? Because it turns out that this kind of algorithms would give rise to these umbrella configurations. So I have a bit of time, maybe I can tell you why, right? So the reason it gives rise is that you do this kind of mental experiment where, again, you think of these columns as coming to you one by one. So for a while, I give you like the columns of the matrix, and then at some point, I'm going to branch into a bunch of independent instances where I start giving you like columns of instance one, like columns of instance two. So it's not a single instance, it's going to be a bunch of correlated instances, right? And then it turns out that because of the symmetries in this algorithm, if I look at the output it's supposed to produce on the first instance, on the second instance, on the third instance, it's going to be like an umbrella, right? And there is an extension, that's what they call the ensemble multi-overlap gap property, which says that like even if I give you this kind of multiple instances, then this is still unlikely to exist. Somehow, like when you do the calculation, like the hardest case is having a single instance. So it's some calculation that you do. It's not terribly interesting, but that's the argument. Somehow you do this mental experiment of running the algorithm on correlated inputs, and they produce some forbidden solutions if this algorithm was correct.
There's some smoothness for some reason. That's why you expect to have these.
Yeah, so there is this smoothness in that I can decide where to put this breakpoint, where to branch into different solutions, right? So that's where the gap is going to happen.
But your input A is random Gaussian matrix.
It is, yes, and it's important that it is for this. So this theorem only holds for random Gaussian matrices.
But what you described was like after a few rounds, and then the later vectors are coming either from instance one or instance two.
They're all going to be correlated random Gaussian matrices. Okay. All these instances.
Okay.
I mean, don't you just take two matrices and then the first rows come to the first and the rest come to the second, and you look at all possible switching points?
Yeah, so here it's something like that. It's first of all, it's not the rows, it's the columns. Right, so, but then like you, at some point, right, after some column, then you split it into independent instances. So they're going to be correlated via the first part of the instance, yes. So that's kind of the logic, and you know, as you've all said, there is like all these other algorithms for which you can try to do similar arguments.
So the explanation again was that, can you say again why these umbrellas are related to this kind of stochastic algorithms, and
why would a stochastic algorithm produce an umbrella? So in this case, well, because it's an online algorithm, right? When I give you the shared part of the instance, they're all going to produce the same outputs, right? That's kind of the stem of the umbrella. And then at some point when I start giving you independent instances, they're going to start producing independent output bits. So here you have to use a bit about the symmetry of the instance, because like this is a Gaussian, like if I like flip the sign of the column, like the sign of the output can flip, somehow I can force the algorithm into giving me like independent outputs on the independent instances. And then the second part is going to be totally independent. So that's going to be like the, the uncorrelated part of the umbrella, right? So
the umbrella is always about correlated instances?
It's always about
I
correlated.
think like you have two independent inputs, and that's like two of them, and then you do this hybrid, and because it's smooth, then you get something in the middle. That's the idea.
Yeah.
So it's really something about robustness, continuity.
Yes.
All these notions of the relationship between input and output.
Yes. Yes. Yes.
Yeah.
There's specific properties about these algorithms, right? I mean, there are many non-robust algorithms. For example, this technology doesn't apply to like algebraic algorithms, to Gaussian elimination, right? Because they break this intuition. So it's really about specific algorithms. Good.
So one online algorithm could be like you store everything and solve a offline algorithm, right? So what does your
So it doesn't predict anything about what such an algorithm would. So it's not, it's not a universal hardness result. It doesn't say that if you solve it's not a reduction. It doesn't say that if you solve this, you have solved something else. It says this specific class of algorithms, including the one that I gave you as an example, cannot do better.
So what will be the assumption on this kind of algorithm?
Right now, I'm just assuming it's an online algorithm. More generally, it's any kind of algorithm that I can force into producing these umbrella configurations, right? So people have studied it, like there is local algorithms, there is low degree algorithms.
Okay.
Yes. Yes. Yes.
For these predictions, is it important for any reason, like how large of an umbrella you have? Like how many points are involved?
Good question. So if you want to be like completely asymptotic, right, this is why I'm going to sort of fix alpha and let n roam free to infinity. Then I don't think it matters. How many?
You could focus on just ones with 3 points, or?
Well, I mean, how many points? So it's right. So this kind of theorem, right? For this problem, we can only prove it provided that the umbrella is sufficiently large. Provided, so like the statement of the theorem says that there exists some R that depends on all these parameters that I told you about, for which then our umbrella doesn't exist. Okay. Right? So there is some quantifier there that I'm hiding, right? So in the end, the statement would be that like once I fix all these parameters, alpha, beta, blah, 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 R, and then I let n go to infinity, there is going to be some sufficiently large value of n for which the algorithm will fail.
But in some other cases, you need the number to increase to get the better hardness.
Yes.
But
yes.
You don't get anything if you're showing n dimensions to square root n dimensions.
I don't think this argument tells you anything for that range of parameters, right? So in some sense, we have like, we have one where in the regime where it's constant, right? And then you let n go into infinity, and these kind of lattice reductions tell you what happens in the regime when n is, when m is very small compared to n. This kind of middle range, like you say square root of n? No, I don't know. I don't have like a proof about what happens there. I suspect that if you just care about online algorithms, you can probably rule it out from first principles, right? So that's one thing that you might be able to do. You don't have to go through the route of OGP and everything. But in general, yeah, somehow this technology is not so well equipped for dealing with these kinds of questions. As far or maybe my knowledge is like limited. Maybe you can do it. Good.
Does it suggest any LWE problem that should be hard, like that?
Well, the LWE experts don't seem to. It is kind of like that, but in their reduction rate, they have somehow I don't know, it has to do with like the length of the entries growing. So it's in some regime of parameters that LWE hardness doesn't really cover.
Right, so maybe it's like a different regime that wasn't studied.
It is a different regime that wasn't studied, but so reductions in this regime are not useful, and that's precisely why somehow like alternative hardness arguments might be interesting. So it's some other way of arguing why it might be hard. Good. Yeah. So great. Like I'm very happy with all the questions I got. Right. So summary. Right. So what did we do? Right. We studied this problem where given a random Gaussian matrix, I want to find some kind of discrete vector in the grid that makes this small. So I gave you like a couple of algorithms, which essentially is like adapting some algorithm of Bansal and Spencer, where they had ±1 inputs and they wanted to bound the infinity norm. And it's a bit simpler, but the idea is from there. Hardness, right? So the lattice hardness is essentially like something from the CLWE of Bruna et al. Overlap gap property, like for B equals ±1, it was done by Gamarnik et al. And then I told you about this cryptographic hash, which our co-authors Vafa and Vaikunathan came up with in like a previous paper also. Like the idea was essentially there. So what is new here, right? And For me, I think like what I find very interesting here is two things. First is that there is kind of this emergent hardness is something which should not be hard at all, right? I do like a random linear map. There is no hardness there, right? And then like by the very virtue of having to implement it, you have to discretize input, you have some cryptographic hardness emerging. So I think it's quite interesting that it's not like, and it's like the question you ask, right? Of course, I can design like great hash functions, but those are not natural, right? They don't come out. This is something that, you know, you implement and it might come up and you get some hardness in there. What is it good for? So maybe I'll say a few words about that. And and the second thing I wanted to say is that what I found interesting about this problem is that we did not know what the result was going to be ahead of time. We did not know it was going to be square root of alpha over b. And this kind of leads me to, you know, this picture about like when I was at the AS 20 years ago and I learned complexity theory from Avi, like this was the picture that we have. Like there's the algorithms guys, they design algorithms. And there's the cryptography people, they design like secure computation. And then complexity theorists, we're the police, right? We decide somebody gives you the problem, does it go on this side or does it go on that side, right? You kind of know what the answer is. And you know, and then somehow like people were really successful, right? And Irit had her big result back then at like these vast predictions about what kind of PCPs, like if I set this parameter to be like epsilon smaller or epsilon larger, you're on this side or on that side, right? And that was the world. And now like what I have kind of seen, you know, happens more and more is that people kind of give you these problems for which you don't know, you have no idea which side they're on. Like complexity theory doesn't really tell you the answer. It's a bit more like this, right? Like kind of everything got eaten up by machine learning. And then I think it's a real miracle that like there is this island crypto that survives. Why does it survive? Like we have some idea why, right? But we don't really understand, right? Where do you draw the line? Right, and that's why I think it's kind of, you know, we don't really have good theories to explain it. We're at the stage where you kind of throw it everything you have and you hope that, you know, something sticks. And you know, there is a lot of these kinds of problems where you change this parameter a little bit this way or that way where you don't know how it's going to be. So that's what I think is interesting. And just to tell you, okay, 2 more minutes. Sort of, we kind of in this context we had like we are working on like some follow-up work on this where we asked the question, well, you know, maybe can this have some applications, right? So what this tells you is that if I have a random matrix, like inherently it's hard to find collisions, but can I like do something where I know a collision but you don't know it and exploit this to my advantage? And we have some work where we kind of show that you can do this, is that you can sort of sample a Gaussian matrix together with some kind of hidden short input so that you know some output which is very short, which is close to the statistical threshold, like a bit above the statistical threshold, but way below the computational one where you can find collisions. And we can do it in a way in which the matrix itself is statistically close. We can prove it's statistically close to like an IID normal matrix, right? And so this is my opportunity. My secret has always been to, when I give a talk in front of application people, I pretend I'm a mathematician. Here I talk to mathematicians, so I'm going to pretend that I do applications. And so this is sort of the picture that we have, right, is that so what our co-author Nikon Waffa did, so he took this, he trained some neural network on some, but he fixed the first layer to be this Gaussian matrix, right? It's a contracting Gaussian matrix, right? And he planted this solution inside it, and he trained it to recognize, I don't know whether it's a shoe or whether it's, I don't know, like some fashionist data set where it's supposed to classify things. And what he can do is he can say, well, I have this backdoor, right? I can plant this backdoor so that when I can change this image dramatically so that the algorithm doesn't know, right? It still thinks it's the same thing because like the outputs are very close to one another, but it's actually, even though it's visually very far, right? This would be something which would be in the same class of it. But if I measure how far it is, like the output, this would be much farther in the output domain, in the output than this.
I don't understand.
Yeah.
What's the third picture?
The third picture is just, well, it's a quality. I don't even have the numbers here, right? So if I look at the distance between the outputs, it's going to be much closer between these two than between these two, right? So there are two inputs that look very much alike, but their outputs are far, like they're natural inputs. But now if I do my planted collision, then I get them to be very close.
Yeah, but would you like a natural looking background? Would we like
Yeah, I don't know if we can do natural looking, like this is some random vector of pluses and minus ones, right? Or plus and minus some entry.
I mean, you would like to be able to modify a given input. So
Yeah, this we don't know, right? It's, yeah. After all, we are theorists. Yeah, this is the best we can prove it works.
Curiosity, you plant the vector,
Uh-huh.
and then you contract, and then
Yes.
you train some.
Yes, yes.
So this is assuming that when you train on two very close inputs, they end up in the same class. This is kind of an implicit assumption here.
An implicit assumption is that for typical close inputs, they end up in the same class. Yes, I think they have these adversarial attacks where you can change the inputs adversarially, where they don't end up in the class. But it's a network that's being trained to kind of behave well on natural inputs. Now, like creating adversarial inputs is, I guess, what people know how to do. But here I have a backdoor. I have some kind of ability to do it to any image that you give me in a way that will make it think that it's close. Yeah. Yes.
Going back to this padding thing, you said padding with 0 doesn't work, but if you pad with something nonlinear, like a signature, something like that, then you couldn't change or kind of anything.
If you put with the signature, and then you train it on the input together with the signature, but so then, I see. So then, the map is a contract. It's a good question. I don't know. Yeah, it's.
Yeah, but then when it's satisfied of the requirements for hatching, like it will be locality sensitive.
It's for sure.
You're essentially changing the input domain with the signature, right? And now the question is, what does that do? Yeah, I don't know. I'm not going to try to answer the question here, but it's a good idea.
So just to kind of understand this picture, if I were to really just like put random noise on this left picture, you expect
things will like very far. The outputs will be very far. But here is some kind of noise that I engineered together with the input, right? Which makes them these two things hash to values that are very close to one another. So I create like near collision, which I shouldn't be able to do computationally,
right?
Because of
But kind of, can you say something like if I didn't know this matrix from advance, then like from somebody who's just like looking at these two things?
No, if I don't know this matrix in advance, then somehow like our result says that it's not possible. So here you have to sample the matrix.
What I mean is that you know the matrix from in advance, so you generate this noise. But if I don't know it, then this should look random to me in some sense.
It's statistically close to being a random matrix. Yes.
I mean, the noise is statistically close to be this random noise.
The noise is uncorrelated with the matrix. So I can sample a matrix together with a short input, right? So that AX is short, right? But
so X is like X is random.
X is random, yeah.
Okay, awesome.
Okay, thanks so much.